There. Can you hear me? Are you muted? You are muted.
You are very loud.
I'm
I am turning my volume down.
okay. Yeah, yeah. It's not like I'm loud compared to anything else because there's nothing else here. There's just us. Is that working?
Okay. Yes, I just need to figure out where the volume was.
Hey Pamela. It's been
Hi.
it's been a week.
It has.
And last time we saw our heroes, I was in the YouTube studio in Los Angeles.
And I was in the exact same place.
Right. And now I am recovering from a week spent filming from early morning until evening, and yeah, we're pretty ruined at this
But
point.
you had fun.
Oh, we had super fun. Yeah, yeah. It was really, really good fun. We had a chance to interview probably 12 different people over the course of the week. We interviewed Mike Brown from Pluto Killer, Mike
Yeah, yeah.
Brown from Caltech, Heather Knutson from Caltech, Mark Miller. And one that you'd be a little jealous. We got to interview Andrea Ghez from UCLA, which I know she's one of your heroes. So
I wouldn't go so far as heroes, but she's someone who I totally admire. Hero is like the next step up.
yeah, yeah. All right. Well, anyway, just hearing her stories about how she uncovered the supermassive black hole at the heart of the Milky Way,
Yeah.
and literally that's just all she thinks about is just that just that region just around the supermassive black hole. And it was really neat to talk to her, and just a great person to interview.
Yeah,
Of
she
course, we
really
got a chance
is.
to talk to Dr. Thad Zabo and Ian O'Neill, and that was great. And then we got a chance to do a live episode of the Weekly Space Hangout right in the studio. And of course, we did a live episode of Astronomy Cast last week right from the
Yep.
studio. So yes, it was great. And again, a big thank you to everyone at YouTube for letting us use their facility for the last week. It was a real treat to see how grown-ups make videos.
And it was an opportunity to learn that you are actually just pink, and it's not the fact that there's a blue wall behind you. Even well lit, you were slightly pink.
Yeah, yeah, I know. I run a little pink.
It's okay.
But I do have a blue wall. So, right. So, if you've never seen this before, what we are doing is a live episode of Astronomy Cast. We're going to be doing episode 321, which is on solar flares. And we'll take about 30 minutes to do this episode, and then we will stick around for another half hour and answer your questions about space and astronomy. So, regarding answering your questions about space and astronomy, there's a few places you can do that. One is you can do that from the YouTube page. So if you're watching this over on YouTube, you can post some questions there. You can also post some questions on the event page for this on Google+. And the last place you can do this is over on, I should post this on Universe Today. Okay, I'll do that in a second. And the last place you can do this is on, so there's a new method that Google+ has. So if you're watching this on my stream, then you can post your questions there, and I will try to spot them.
But really, YouTube is the best place, and your efforts can work to single-handedly improve the quality of comments over on YouTube.
Well, the whole new Google Plus integration of comments is going quite hilariously. So I don't know. Have you seen the
No.
outrage, the pouring of outrage? So they've switched all the YouTube comments over to Google Plus comments.
Right, so I knew that.
And people
Wait,
are.
did that retroactively work too?
Well, I don't think so. So it kept all the
Okay.
old comments. But boy, are people mad. I'm not mad. I think it's fantastic.
Yeah.
And in fact, because not a lot of our viewers really complain because our viewers are also used to Google Plus and they've been working
And they're
with that
not trolls.
and they're not trolls, yeah. And so you look at the complaints of the people on the post where Google announces that they're switching these comments over, and it is just the worst vile comments you can imagine. Like you need a shower after you read this stuff, and so you're like, the irony is lost on them. So anyway, I think it's a good move. It's a little rough around the edges so far, so it's been really hard to find where the new comments are showing up because they show up as notifications
Yeah.
in Google Plus, and it's a little still not working very well. So. But overall, it's absolutely the right direction. They just need to smooth out all the bugs. So
Turn on all the push notifications on your phone and everything will just go to your phone is what I've learned. You'll drive up your data consumption, but At least you won't miss anything.
Yikes. I forgot to do one thing. I apologize.
And suddenly mad typing commences.
Done. Okay.
Okay.
Okay, cool. So you ready to go?
I think so.
Okay. Anything to announce this week?
I will be in Indonesia next week. But that's not relevant because this will go live while I'm there. So
right, but that means that we're going to record something later
randomly this week.
Yeah, okay.
Probably Wednesday.
Okay. Thank you for the notice.
I will give you better notice once I've looked harder at my calendar. I'm simply realizing tomorrow is impossible.
Yeah, just as long as it's after 11.
Okay.
Okay. Well, then let's get rolling.
And welcome to the sausage being made.
Yes. Yes, you can see how this... You actually get to see us negotiating recording times. Okay, well, I'm going to click record.
Okay, I'm clicking record. I'm waiting for my computer to do something. It's thinking. Hold on, I had fail.
Wah, wah.
Yeah. Okay, now it's going. Now it's happy.
Okay, mine is still recording. So.
Sorry, Preston.
Here we go. Astronomy Cast, episode 321, Solar Flares. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. My name is Fraser Kane. I'm the publisher of Universe Today, and with me is Dr. Pamela Gay, a professor at Southern Illinois University, Edwardsville, and the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. How are you doing, Fraser?
Good. I'm just returned back from a week of recording video down at the YouTube LA studios, and so we've got tons of good stuff, and that'll all be appearing in the YouTube feed and on Universe Today over the next couple of months, probably.
And you got to experience what it's like to record in some place that is not only warm, because I know we both freeze to death in our studios, but also had like all the bells and whistles, which is kind of awesome.
It was great. It was just amazing to be able to use all this great gear, cameras, lighting equipment. It was great, and I really appreciated their assistance as well when we didn't know what we were doing, which was most of the time. So hopefully this will allow us to provide more professional recording type stuff in the future.
It's a goal.
It's a goal. Just as a reminder to everyone that we record Astronomy Cast every Monday at noon Pacific, 3 Eastern, as a live Google Plus Hangout on air. And you can find that video in a bunch of places. Over on Universe Today we post it, on Google Plus, on YouTube, on CosmoQuest. So if you want to watch us live and then interact and ask us questions, you can do that every week, Monday, except for next week when we'll be recording at a different time. But normally every Monday at noon. All right, let's get rocking with the episode. So sometimes the sun is quiet, and other times the sun gets downright unruly. During the peak of its 11-year cycle, the surface of the sun is littered with darker sunspots, and it's from these sunspots that the sun generates massive solar flares, which can spew radiation and material in our direction. What causes these flares, and how worried should we be about them in our modern age of fragile technology? Let's talk about solar flares. And you could not have timed your selection of this episode any better, because we are just experiencing a gigantic sunspot cluster, AR 1890, and it has been firing off material in our direction.
It is flare happy, and this means if you have any flights upcoming, make sure you figure out which side of the aircraft is going to be the north side of the aircraft if you're flying after dark, because these aurora are absolutely amazing to watch from an aircraft, and you couldn't get a better time to see them.
Yeah, absolutely. It's an absolute treat to, especially because a lot of, like, if you're going to fly from, say, New York to Europe, you're going to go Great Circle route, you're going to go past Greenland, and you're going to get a view. So absolutely, if you're going that way, try and take the left side of the aircraft.
Chicago to Beijing, right side of the aircraft.
Yeah. So figure that out. So let's talk about solar flares then. So what is the underlying? I guess what is the series of processes that lead up to us seeing a solar flare?
It's basically a fairly simplistic process to try and explain and extremely complicated to mathematically model. What's happening is as our sun is working on turning its magnetic fields inside out, as it's working to make its north magnetic pole its south magnetic pole, or its south its north, however you want to look at it, it reaches this phase at what we call is solar maximum. And during solar maximum, a bunch of the magnetic field lines, the lines of force along which particles flow, end up forming helixes that pop out through the surface of the sun. And where they pop out, we see these darker regions, these sunspots or sunspot complexes. And these field lines, they contain vast amounts of energy. And sometimes these field lines realize that, hey, we'll be at a much lower energy if we break the top part of our coronal loop, this loop of helixed magnetic lines that come out the surface of the sun and basically form giant arches. If we break off the top section, set it free, and reconnect closer to the surface of the sun. During these magnetic field line reconnection processes, all of that energy that was trapped in that magnetic field, that tube of plasma, suddenly gets released. It becomes kinetic energy, it becomes thermal energy, and all of that goes firing off. And in some cases, it gets fired off straight at us.
You know what's one of the best experiments that you can do to sort of show this process is take spaghetti and bend it and break it. And I forget the exact physics that make this happen, but you will always get a chunk of spaghetti flying off.
Stress and strain.
Yeah, and it never just breaks. It
No.
always fires off a chunk of spaghetti out, and you'll get like one or two pieces that will head off in one direction just because of the physics involved, the forces and the stresses and stuff. So you can imagine, you can fire chunks of spaghetti at your friends with, and you say, I'm just making solar flares. It's just a science experiment. Right. So you get these disconnections and reconnections, and then you get this release of energy. And so, on what order? How much energy are we dealing with here?
This is one of those things that when I started looking up the energies, it was really kind of mind-numbingly large. I'm in the process of pulling up the numbers, so if you see me looking in strange directions, it's because I want to get this right. So it's the equivalent of millions of 100 megaton hydrogen bombs exploding all at once. It's a little less than 10% of the sun's solar output per second. So when you start thinking about that, that's a pretty huge number. That's like Earth destruction number, but luckily we're far away.
Yeah. 10% of the sun's entire output for a second is released in one little spot.
And when this energy is released, it fires off protons, electrons, basically ionized particles, things that have charge. And this is where it gets interesting, because a charge in motion generates its own magnetic field, and those charges in motion end up hitting our own Earth's magnetic field.
So how long does this process take? Like, say you've got these magnetic field lines are starting to twist up, and then you get that event. How long does that whole process take, but then to sort of get to the Earth?
Well, it's only a few seconds for the whole arch, the loop of twisted magnetic field lines to break and reconnect. But then the light travels towards us so that we can see this happening. That travels at us, at the speed of light. So about 8 minutes later, we see what has happened. Some of the satellites that are closer to the sun than us will see it first, but we still have to wait for their information to get to us at the speed of light. So we're not going to find out about this in anything less than a little over 8 minutes. But then we have to wait for the particles themselves to get to us. And the particles, luckily, are not traveling at the speed of light. In some cases, they're traveling faster than others, but in general, you're looking at several hours. Now, where it gets a little bit squirrely is our best indication that, oh dear, the Earth is about to get hit, comes from a set of geostationary satellites. These are the GOES satellites, which highly amuse me with their naming scheme. They're the geostationary operational environmental satellites. They're constantly watching both down at the Earth to measure weather. And before they get launched, they're named letters. So goes A, goes B, goes G. Last year they launched goes P, which is my most favoritely named satellite. But once they're on orbit, yeah, you have to giggle at that one. But once they're on orbit, they get renamed with numbers. So we've had goes 1, goes 2, goes 3 orbiting the Earth. And these satellites being up at geostationary orbit, they're significantly higher up than the space station, than the space shuttle, or was the space shuttle, now Soyuz. And they detect the particles coming towards the Earth a little bit sooner because they're further out. And they can provide the astronauts all of about 15 minutes warning that they need to seek shelter. Something really bad is coming.
Now, why would the astronauts need to seek shelter?
Well, these high-energy particles, they can cause severe damage when they start hitting your molecules. This is a form of radiation. This is actually one of the major reasons that we're worried about keeping our astronauts safe if they go on a mission out to Mars. Here on the surface of the Earth, we're well inside the Earth's magnetic field. We have a big atmosphere above us. All of these different things work to either redirect the streaming particles or to protect us from the high-energy photons that they release. We're safe on the surface. The astronauts are up above a lot of the protection, and they can get zapped in ways that could increase the probability of cancer and otherwise harm their DNA.
Now, is this an issue for the astronauts on board the International Space Station? Because it orbits much lower, right? And it's protected by our magnetosphere.
It's protected by Sorry, Preston. It's protected by our magnetosphere, but it's not protected by our atmosphere. So if you have X-ray photons, those are quite happy to go through things like, fiberglass. So they'll get stopped by metal shielding, they'll get stopped by other things, but the highest energy photons that get released, those are going straight for the astronauts through the outer shell of the space station in some areas. There are regions that they can go into that are safer, and that's where they go when there's really bad events.
But the real risk is for the folks who would leave the Earth's orbit and go to the Moon or Mars or things like that, right? I mean, they're really exposed.
Right. So it's the space between here and Mars that is the most dangerous. If you're on the Moon, you can go under the surface. If you're on Mars, you can go under the surface. You always have some hole in the ground that you can climb into if you need it. Between here and Mars, you want to have as lightweight a spacecraft as possible, which means you're probably not going to have a big lead shield all around you, and you're probably not going to have a big water layer between you and the outside of your spacecraft. All of these extremely heavy things can help to protect you from the radiation, but they weigh too much to support taking them all the way to Mars.
Yeah, and I know that the astronauts, when the astronauts went to the Moon, they actually were really fortunate that they avoided some of these major flares. They were there when it was quiet, but before and after there was some pretty bad flares.
Yeah, there was at least one Apollo mission where it was just a couple weeks before and a couple weeks after there were some big X-class flares that could have seriously harmed the lives of the astronauts. And at that point, we didn't necessarily have all of the GOES satellites giving us early warnings.
Yeah, this is a really new development, is that we have this monitoring system so that we can see these flares on the sun and then take action. Like, I guess you see the radiation and then take action before the particles arrive. You got this gap, right?
And in all honesty, GOES wouldn't have helped with the Apollo missions because geostationary is inside of the Moon's orbit, but we also have things like Solar Dynamic Orbiter. We have a whole series of satellites out there monitoring the sun. The stereo missions, the numbers just go on and on.
Yeah, and the worse the flare, the less time you have, right? Because there's more energy boosting the particles out.
Well, it's a combination of, yes, there's more energy, how it's released, but you can spread that energy over a larger area, or you can concentrate it in a smaller area. So when you use words like big, that's not the clearest word, because you can have this big giant thing, but the flux over any small area is much less. So when we start trying to figure out, is this a big flare, is this a small flare, what we actually look at is the flux over a set region as measured by the GOES satellites at the distance of, well, geostationary orbit above the Earth.
Well, they have a method for classifying flares, right? They have a actual, like, was it MX? Different kinds. Yeah.
And this ends up being, so they make estimates of how strong they think the different flares are going to be based on what they see, and then they classify the flare finally by how strong it is when the energy hits the Earth's atmosphere. So this is where you start looking at watts per square meter. They look at it in the 100 to 800 picometer wavelength of the light that's coming. And it's actually measured by satellites in geostationary orbit of the Earth. So they do make estimates based on what they see, but the final measurement comes from the flux that's hitting at geostationary orbit.
And so what is the I guess the measurement system, like we have, like with earthquakes, right? You've got the I guess before it was the Richter scale, there's a new scale. But you got tornado scales, you've got hurricane scales.
Right. So just like with the Richter scale, and just like with the magnitude system we use with our eyes, this is a logarithmic scale. A is the wussiest. It gives off 10 to the minus 7 watts per square meter. So if you imagine a millionth, basically, of a 1 watt Christmas tree light, or I guess a 10 millionth of a Christmas tree light. That's how much light you have covering a square meter. Then 10 to the minus 7 to 10 to the minus 6, that's a B-class flare. And then the X-class flares are ones that are 10 to the minus 4 watts per square meter. So the amazing thing is, these things aren't even giving off as much light as your faintest Christmas tree light with its energy spread out over an entire square meter. But when you start looking at the size of the Earth's atmosphere, there's a whole lot of area to be collecting all of that wattage. And it adds up. And all of these moving particles, they create changes in our Earth's magnetic field. And here's where it starts to sound a little bit like turtles all the way down. So you have moving particles coming from the sun. Moving particles generate magnetic fields. The magnetic fields from these particles cause variations in the Earth's magnetic field. When the Earth's magnetic field varies, you end up creating, well, in this case, current, and that current just happens to be in places like, the power grid on the planet Earth. Wires are very good at carrying current that's generated by changing magnetic fields.
So what's the most powerful flares that are sort of possible?
The most powerful one that's been measured so far is one that occurred, it's called the Carrington flare, and it occurred in the 1800s. In fact, it occurred on September 1st, 1859, and there's a well-to-do scientist, a gentleman scholar, you might say, 33-year-old Richard Carrington, and he was at the time England's foremost solar astronomer, and he got up in the morning and he was happily making his daily measurements, and there's this amazing sunspot cluster that if you look at the images, science.nasa.gov has them posted, and they're stored by the Royal Astronomical Society. It looks more like a sea serpent or a whole bunch of slugs come together than like your classic single or double sunspot. It's this amazing system. And at 11:18 in the morning, he saw where the sunspot that he was sketching was suddenly flashed out with white light. And that is significant because the majority of the energy given off in solar flares isn't in white light. It's in much higher wavelengths of light that aren't visible to the eye. He saw a white light flare in his projection of the sun, and he went to go get a friend to witness it with him so that it wasn't a lone account. And just 5 minutes later, when he returned with someone, it was already starting to fade away. So this amazing flare that was visible in white light, the next day created aurora borealis and aurora australis that reached all the way down to places like Jamaica and Cuba, places that normally never get to see this. So this was the biggest flare that anyone has ever seen. And what's kind of remarkable is if you take Arctic ice cores or Antarctic ice cores, you start to see the history of solar flares recorded in the ice, and this is a once in 500 years event. No other flare in the 160 some odd years of visual observations or in the 500 years that we can measure through the ice has compared to this. And in fact, it's more than twice as powerful as the next brightest flare.
Wow.
Yeah.
Well, I know the one that was fairly recent, we had one a couple of years ago, and it was like an X28 flare.
Right.
And
that was the one that took out the power grid.
yeah, and I've heard that
awesome
one in the 1850s was like an X40.
Right. So the one that you're talking about is the March 1989 geomagnetic storm. So it makes us old that seems like just a few years ago.
Yeah. Well, but I mean, yeah, I remember it happening.
Right.
We had a big problem in Canada. We had this. I'm trying to remember.
It's referred to as the Quebec blackout.
Yeah, that's right. Yeah.
So this was when we learned for the first time, really, and we knew from the 1859 event because it actually caused telegraph wires to set paper on fire, and they disconnected all of the batteries from the telegraphs, and they were still able to send messages through the wires. But this was the first modern history one where everyone was relying on electricity, and this happened. So the problem is the power grid in Quebec was running at pretty high capacity, and you can only send so much electricity through the wires before they start to do things like melt, like change length, stretch under their own. So as they stretch, as you heat them up, they'll eventually even just break. And so in this case, they overpowered the Quebec power grid and sort of took out power to a large chunk of the Northeast Corridor.
And so this is, I think, the big issue. I mean, when you think about these horrible blasts of radiation coming from the sun, and you wonder, like, are we going to get irradiated? The answer is no, thanks to our atmosphere. But it's this impact on our technology that's the problem.
Right. And you have to worry about what happens if this sort of sudden blackout happens and it's winter and there's people relying on electronic heat. We learned during the more recent 2003 blackout, which was caused by tree limb on wire and a faulty alarm going off, that if you knock out the power for the Northeast, Canada and the United States, it can take as long as 2 days to get that power back on. Well, in the summer, you just sweat a lot. But in the winter, that can become deadly because not everyone has fireplaces anymore. And
Quebec is not a nice place in the winter time without power.
Right. And so we have to really start worrying about northern China, about northern Russia, about Scandinavia, Iceland, and all through Canada, Alaska, and the northern United States. And it's in these northern extremes where the winter is so much worse that our power grid is the most fragile.
But I mean, it's more than that. I mean, we've got these telecommunication systems, we've got communication satellites, we've all got these computers that sit in our pockets now.
And these X-class flares can take out a satellite now and then if they're particularly strong. All of that X-ray energy, that can knock out sensors.
Yeah. So I think that's the big risk. Now, our sun is a minor dwarf star. Is it a G dwarf star?
It's a G star, main sequence, everyday star.
But the solar flares change with the different kinds of stars, and we've talked about like red dwarf stars. They have totally different kinds of flares, right?
Right, and in fact, depending on what phase a star is in, they're all generally called flare stars, but they have different subclasses. And one of the nastiest stars for a prolonged period is those red dwarfs when they're quite young. they'll go through a couple billion years of giving off massive blasts of X-rays, such that any planet that was in what would otherwise be known as their habitable zone would simply get irradiated into oblivion. And that's long enough that your planet is formed, is sitting there, and any life on it gets destroyed before the system really settles into existence.
And then what about some of the bigger stars, like the big
So
Eta Carina, things like that, right?
Well, so Eta Carina, it's not so much a flare star as it's undergone various nova over. Well, it underwent one big brightening in the 1800s. But we have other things like UV Ceti stars. These are stars that when you watch them, they give off these sudden brightening moments that are quite brief. And we believe that these are flares just like our sun experiences. We're able to observe sunspots on other stars. We have no reason to believe that these parallel brightenings aren't a parallel event caused by flares. So it's neat to see that the physics that applies to our sun applies at different scales in other types of stars all across our universe.
So, we've done a whole show on the Aurora Borealis and Aurora Australis. So, if you want to go back and get more information about how to see the Northern Lights and what the mechanism that's going on there. But just sort of as a refresher, if people want to be able to see the Northern Lights thanks to these flares, and especially now that we're in this solar maximum time, so this is your chance. So what should people do to sort of get up to speed on what's going on? And it's great new technology now.
Well, the best thing you can do is keep an eye out on solarweather.com, or spaceweather.com rather. That website will always keep you up to date on where the best auroras are likely to happen. And if you find out you're in a region where there's a likelihood of seeing aurora, get out of the city lights. Find some place that doesn't have that much light pollution, or make sure the light pollution is on the southern horizon, and then look north and watch for streaks, for curtains, for all sorts of amazing glowing movement along the horizon, and sometimes all the way up to the zenith. It's really beautiful to watch.
Yeah, I mean, even since we've been recording this show, the technology for tracking them and predicting them has gotten a lot better, and that information has even really gotten disseminated out through the internet. So there's apps you can use, and maybe people can make some recommendations of what they've used, but there's apps you can use that will give you predictions, when it's time to go see some aurora. So it's pretty amazing now what's possible. So if you live anywhere north of, I don't know, like what, Chicago, even more south than that.
Yeah.
I mean, you stand a chance of being able to see one, especially during this solar maximum.
The best shot is always in Scandinavia and in Alaska, but really anyone from about Boston, London, northward, you're probably good to go. But this is where I'd say also go back and listen to our show on coronal mass ejections, because solar flares do have a bigger, badder brother.
Yeah, absolutely. Good. Okay. Well, was there anything else you wanted to bring up this week?
No, I think that's about it.
Awesome. Okay. Well, thank you very much, Pamela.
Thank you.
All right.
And we save. And if any of y'all have questions, now is the time to leave them, preferably on YouTube, because that's the best place to find them. This is where I try and figure out who is texting me.
I heard that.
Sorry about that.
Okay. Well, I'm going to start with some YouTube questions here.
Okay.
Let's see. So Polygona9 asks, what would happen if the sun stopped turning? What impact would that have on solar flares? It would stop them, wouldn't it?
It wouldn't stop them immediately, because the outside of the sun and the inside of the sun don't rotate at the same rate. But if you stopped the sun all the way through the center, so there was zero rotation, I'd love to know where you put the angular momentum, but ignoring that, yeah, it would stop the solar magnetic field and stop flares and stop the solar cycle and just stop.
Yeah, because I mean, a lot of that's just all about different amounts of rotation, right? And the interactions.
any rotation is going to generate a magnetic field if you have charged particles.
Right, and so if it all just stops and just, I mean, you could probably get small localized stuff, but you wouldn't get these big reconnections. That's really interesting.
Well, and what's kind of neat to think about is our moon has frozen in place magnetic fields where particles got aligned in rocks from when there was more molten rock and more magnetism on the moon. So there's residual magnetic fields. Mars has some residual fields as well. But because the sun's a plasma, it's not going to have any residual fields the way the moon and Mars do.
Joseph Romero says this is his first time watching us live after listening to us for 6 years. So
welcome.
Welcome, Joseph. Let's see, what else we got now? And Richard Drum is watching us live.
Hi, Richard.
How awesome is that? Richard helps us out all the time for all kinds of things, but specifically he's been extracting out the audio and editing some of our live stuff and putting it into the Astronomy 365 feed.
Yeah.
So, and he's the one who hooked me on meteorite collecting, so it's his fault.
Yes.
Yeah, and Richard says that this show will also be available as a 365 Days of Astronomy podcast on Monday the 18th. So a lot of the stuff that we do goes out that feed as well. So the Weekly Space Hangout is out there, the Learning Space, I think.
Yep, everything we do goes out that way.
Yeah.
So check out 365 Days of Astronomy and get many different fixes, many different voices for your astronomy addiction.
Tommy Dog on YouTube asks, what effect is the solar flare class X that happened yesterday going to have on us?
Beautiful aurora. We're already starting to get photos coming back.
Yeah. Okay, Mike Hunt asks, I have a question for anyone in the chat, but I'm going to fire this question to you, Pamela. I keep hearing that the galaxies are moving away from each other and the space between is expanding. How come we're going to collide with the Andromeda Galaxy?
Oh, that one's actually, people like to confuse other people by explaining this poorly. If you have galaxies that are gravitationally bound together, they're going to continue to interact like normal. If you have a group of gravitationally bound galaxies here and one lone galaxy over here, this one lone not gravitationally attached one is going to get carried away by the expansion of the universe. So since we're gravitationally bound with Andromeda and other local group galaxies, Triangulum, we get to stay bound together and eventually collide. But when we look out, most of the galaxies we see aren't attached to us, so we see them streaming away with the expansion of the universe.
Could you imagine there's some galaxy that's like or two galaxies that are at the perfect distance from each other where the expansion is carrying them away and the gravity is pulling them together and they just remain perfectly the same distance apart?
Well, it's never quite in balance because everything has intrinsic motion. But we do see examples of flows where things, the motion is harder to tell, and you do see these balancing points getting past one direction or the other.
I actually did an episode of the Explainers, I've been running on YouTube, and one is, someone asked me this question, is everything in the universe expanding? And so I go into that. Short answer, no. Longer answer, maybe, thanks to the Big Rip. Okay, let's see. Nope, nothing else there. Eric Williams says, this chat is broken, sorry, although he just chatted.
That doesn't compute.
Silamoran Cecile asks, is this solar maximum a bit different from what you might expect from a solar maximum? Has this period been longer than usual this time?
So we don't know when it's going to end yet. We have to look for the locations of the sunspots to change, and that will tell us how things are going. But this solar maximum has been much wussier, for lack of a better word, much less powerful than past solar maxima, and it took much longer to come out of solar minima than expected. So the sun is definitely quieter this cycle. It had originally been predicted that it was going to be much more active, and so far that just hasn't happened, and we should be coming out of solar maximum at this point.
So take that, 2012 conspiracy theorists. This is a late and lame solar maximum.
Is true.
And we won't know how lame until it completely wraps up. But
Yeah.
so far, but that's weird because we were expecting this was going to be one of the more powerful ones. That was the prediction.
Exactly. Yeah, and it just didn't happen that way.
Graham Sticking says that are solar flares what our stars were in the 1970s?
Yes.
Yes, that's exactly what they were, solar flares. Okay, I got that question. That's over on the Astronomy Cast event. Now I'm going to go to, let's see, I'm going to go to the Google Plus event. Okay, so this is a good question. Hugo Burnham asks, do all other observed stars that have flares also have a min-max cycle like the Sun? Presumably not over 11 years, but at other frequencies.
We have observed stars to have solar cycles that are at different durations. I can't say off the bat that, yes, every single flare star has been identified to have a solar cycle. I don't know. But I do know that there are many stars that have been observed to have stellar cycles of durations other than the duration observed in the Sun.
This is great. So Hugo Burnham says, so a manned future Mars mission would have to launch just as a solar minimum is about to start. And I was sort of talking about the solar minimum. That would be the best time.
It would, but unfortunately things like coronal mass ejections, which, as I said, are the bigger, badder brother to solar flares, they can occur at any time. And it doesn't have to be solar maximum to see them. They can arise without solar activity, without sunspots. They can just manifest and fling deadly radiation out from the sun's surface.
And Hugo's 8-year-old friend just asked, couldn't they just go at night?
Sadly, there's no night in outer space.
There's only day. And Andrew Planet is wondering where the splash screen term that I mentioned comes from. I don't know, we've been using that on the internet. We used to call that the opening page of the website was your splash screen, and then
right.
I don't know where that term comes from. Maybe someone can dig that up for us. All right, I'm going to come back around looking. Susan Murph asks, does the flare have any effect on how many sundogs we're seeing? We've seen a lot this week.
I think that those depend more on atmospheric effects, and we're starting to get lots more ice crystals. But let me double check that. So sundogs are where you see rings going around the sun that often have a set angle away from the sun, what look like secondary bright spots, secondary suns.
I saw a great one in Los Angeles, actually. It was like little rainbows, and there was rainbows on both sides of the sun, when normally you see rainbows on the opposite side of the sky from the sun. But in this case, I could see these two little rainbows on either side of the sun.
Yeah, they're consistently 22 degrees away from the sun. So if you hold your fists up at arm's length together, that will get you how far away from the sundogs are. And they're due strictly to ice in the atmosphere. I don't know about where Susie is, but where I am, we're starting to hit the, oh my gosh, it's well below freezing outside time of year, and thus scarf while recording in unheated attic. And once you start getting ice crystals in the atmosphere, you're going to start getting sundogs around the sun.
Yeah, you're not going to get sundogs from solar flares, though. You're just going to, I mean, it's the regular output of the sun. It's all about the atmosphere. It's all about our atmosphere. It has nothing to do with the sun.
Right.
Would you be able to, but Susie also asked, could I see the solar flares down in Georgia, where she's located?
Check spaceweather.com. These solar flares are big enough that they are going to go further south than normal. I remember, I think it was 2003, 2004, we had a few solar flares that made it as far south as Atlanta. I know Baltimore saw them, so look at space weather and see what the predictions are.
Yeah. Do the poles change during the solar maximum? I guess the poles of the sun.
So they change during the entire process. So at solar maximum is when the poles are most muddied, and then when they're quiet, they're nicely aligned one way or the other.
Joseph Romero says, I've seen something like that around the moon. And that's the exact same thing. That
Yeah.
It's that same process. It's amazing when you think about it, right? That you got these crystals in the atmosphere and they're exactly the right shape.
It's the same thing as raindrops creating a rainbow. So the exact same physics creates the sundogs that creates rainbows.
Yeah, and so you're seeing because the crystals have angles on them that are 22 degrees, you're seeing
it's because the light refracting through the crystals gets bent 22 degrees.
Right, sorry. Yeah, the light gets refracted exactly 22 degrees. And so the light could be going all over the sky, but you're seeing all the stuff that's getting refracted in your direction.
And so someone 20 feet away from you will see the exact same thing. Someone 2 miles from you with the same atmospheric conditions will see the same thing.
From different crystals.
It's the light radiating out just gets bent back to you at that 22 degree.
Yeah, totally. Cool. Yeah, so I think that's all the questions that I've got here. So what's coming up next on the old CosmoQuest info train?
So I think most likely it's going to be us sometime on Wednesday talking about Soho, and then after us at 4 p.m. Pacific, 7 p.m. Eastern, midnight-ish. Am I doing that right? Yeah, midnight London. Then is going to be Learning Space, hosted by Nicole Gallucci and Georgia Basie.
Do you know what the topic is this week?
No, but if you have the CosmoQuest newsletter, it'll say in the newsletter.
Right, yeah. She sends an email out.
Yeah.
And then Friday's the weekly space hangout, and then Sunday's the virtual star party. And I'll be back after not being around for a couple of weeks. So awesome. Well, thank you very much, Pamela, as always. Thanks, everyone, for watching. And we will see you all here next week.
Thank you.
There. Can you hear me? Are you muted? You are muted.
You are very loud. I am turning my volume down.
Okay. Yeah. It's not like I'm loud compared to anything else because there's nothing else here. There's just us. Is that working?
Okay. Yes. I just need to figure out where the volume was.
Hey, Pamela.
Hi.
It's been a week.
It has.
And last time we saw our heroes, I was in the YouTube studio in Los Angeles.
And I was in the exact same place.
Right. And now I am recovering from a week spent filming from early morning until evening. And we're pretty ruined at this point.
But you had fun.
Oh, we had super fun. Yeah. It was really, really good fun. We had a chance to interview probably 12 different people over the course of the week. We interviewed Mike Brown from Pluto Killer, Mike Brown from Caltech, Heather Knutson from Caltech, Mark Miller. And one that you'd be a little jealous. We got to interview Andrea Ghez from UCLA, which I know she's one of your heroes.